All right, Algebra 2, and we're starting the second half of Module 2, or Unit 2. We've been talking about sine, cosine function, or sine, cosine, tangent, cosecant, secant, cotangent for a while now. Now we're just going to talk about the graph of the sine function and how it transforms. First, just some basic information. This right here is the equation we're going to work with today during the lesson. We need to discover how the amplitude changes our graph, how omega changes our graph, h and k change our graphs. H and k are just the same h and k as we learned with parabolas, but we're applying them to the sine function today. As you can see, the amplitude gives a vertical stretch or compression, okay, that way, and omega gives a horizontal stretch or compression. If we have our sine graph, okay, this is our vertical stretch or compression, and this is our horizontal stretch or compression. Vertical up and down, horizontal left and right. A few other things we need to make sure we all understand. What a cycle is. We know what a periodic function is. It's a function that repeats itself. A cycle of a periodic function is a portion of the graph of the function from one point on the graph to the point at which the graph starts repeating itself. And then the period of a trigonometric function is the number of degrees taken to complete one cycle. The number of degrees, either with degrees or in pi. Frequency of a periodic function is the unit rate of the constant rate defined by the number of cycles per unit length. Okay, you're thinking, what? Don't worry, we'll make better sense as we look at graphs and we start doing some problems. Okay, the first thing you see in your classwork are some tables with the A team, the omega team, the H team, and the K team. It was an exercise that I could have split up for you guys to do in class and to divide up the work, but with such few students, I just went ahead and did the work and presented it to you. So I'll need you to fill in the work at the end. You'll see that on this table here, I've done all of the suggested values from your classwork, and we're just going to sort of see how A affects our graph. So first of all, if you look, we're taking this equation here and we're just replacing A. So first, if you see y equals 2 sine x, that's in red, right there. And if I look, the maximum is right at 2, and the minimum is at -2. So the max is plus or minus 2. Here's 3. So our blue one, we're at 3, -3. And then our green one, we're up at 10 and down at -10. So that's what A does. If I look back to the previous slide, we just say amplitude is the distance between a maximum point and the midline. Here for this one, the midline is the x-axis. So the midline is y equals 0. So the amplitude is the distance from the midline to the maximum, or the midline to the minimum. Okay, so for the green one, the amplitude is A. And at the end of this lesson, we have an equation that we can use to calculate the amplitude. Okay, the next set of problems, notice I kept y equals 2 sine x on the graph, just so we had a point of reference. And now we have amplitudes are negative. So let's look at -1 first. -1 is in the yellowy orange. So notice I went down first. The regular sine graph goes up and over. So we start increasing and then decreasing. Increase, decrease, increase. When we have a negative amplitude, our graph is reflected over the x-axis. So if I look at this one, the -1, I'm going down to -1 being my minimum first. Right there is at -1. Note, you always have to look at my scale on these graphs because I zoom in and zoom out with each time I copy it. So -1, so our minimum is -1 and our maximum is +1. -2, same thing with the light blue one. -2 and +2. See how the amplitude affects what we're doing. And remember, the amplitude is the distance between the midline and the maximum or the minimum. The midline here is y equals 0. If we look at this one, we have 1/3. So we still start straight down, but our minimum and our maximum is -1/3 and +1/3. Okay. Oh goodness, sorry about that. I kept that one in there for some reason, but here, again, I'm still comparing to y equals 2 sine x, where the amplitude is 2, and here I have 1/2 and 1/5. I kept my scale the same, so our maximum is 1/2 and 1/5. The bigger our amplitude, the higher the graph goes up and down. So here's the summary of what we looked at for the amplitude. Oh goodness, did it again. This being important, when a is greater than 0, the graph is a vertical stretch of the graph of the sine function, and when a is between 0 and 1, the graph is a vertical compression of the graph of the sine function. When a is negative, it's a reflection over the horizontal axis. When a is 1, the graph is just the basic graph of the sine function. Okay, changing a changes the distance between the maximum and the minimum points on the graph of the function. The maximum and minimum values of the graph are a and -a. Here we have the value, absolute value of a is the distance between the maximum point and the horizontal axis, or half the distance between the maximum and minimum. Okay. If a is equal to 0, then the function's a constant. It's not a sine function because if you plugged in 0 for a, that goes away, and it's sort of silly. You get the line y equals 0. Okay, let's move on. Lots to cover today. Now we're doing omega, sine omega x. Omega is the horizontal compression or stretch. Now we use omega to calculate the period of the function, which we will summarize at the end of the lesson. The period of the function, if I ask you to give me a value, it's 2 pi divided by omega. And then the frequency would be omega over 2 pi. Frequency and period are related. They're inverses, or sorry, they're reciprocals of each other. So we can actually say that omega equals 2 pi over period. Okay, but let's get to this set of graphs. All right, so here I've got sine of 2x, sine of 3x, and sine of 5x. You notice my graph goes from -1 to 1 because our amplitude is not changing. Our amplitude is just the 1 in front of the sine that you don't see. My x-axis goes from 0 to 360, the full unit circle. We aren't doing the x-axis in pies because it was too hard for me to figure out with Desmos, but that's okay. Okay, so if we look at the red one, sine of 2x. So I've got 1, 2. I went through the whole thing twice between 0 and 360. So once, that would be at 180, and then twice. If I have 3x, this is the blue one. 1, 2, 3. Okay, I've squished it in together. 5x for the green. 1, 2, 3, 4, 5. Everything's getting squished and squished and squished. Compressed is probably a better way to say it. I'm still keeping the y equals 2x to give us a point of reference. So 1, 2, it's the red one. Now we have omega as a half and a fourth. If I look at this first one, or purple, a half, so I've stretched things out, okay? Between 0 and 360, I can't even get a full cycle of my sinusoidal function. But if I zoom in a little bit, so you see now I'm at 720, so that's 2 circles. The purple one, I finally get a full cycle in. So omega is a half. I've stretched things out to twice the amount of a regular sine function. And then a fourth, that's the orange yellow one. Again, I can't even see the whole thing. I'd have to stretch it even more. 720 times 2, 1440. So that'd be like 4 times around a circle. Okay, sort of see the point. What about if I make them negative? So I'm still keeping the red one here. So remember the sine function goes up first, it increases. If I make it negative, I go down first. So that's 1 cycle between 0 and 360. Negative 2x, that will give me 2 cycles between 0 and 360. This one was really messy, but I just wanted to go through it because it was just a lot to see, but it's okay. Again, the red one is just my basic sine function that we've been putting on every single slide to compare. Now, if I have sine of pi x, this is the light blue one, I'm right here. Okay, 1, 2, 3. Okay, that's for pi x. 2 pi x, this is the green one. I squished in more. 1, 2, 3, 4, 5, 6. Okay, what do you think I'm going to have here with the purpley one? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the higher our omega, the more compressed we get. The larger our omega, I guess. Okay, now remember if we have fractions, so omega is smaller, it's between 0 and 1, it stretches things out. Our red one is still the sine 2x, pi over 2, that is the black one. Okay, we're not quite there, but if I went from 0 to 720 here, 1, 2, 3. Okay, pi over 4 is the purpley one, 1.5. Okay, so it's stretches things out. Look at our summary. The graph is a horizontal scaling of the graph of f of x equals sine x by a scale factor of 1 over omega. When omega is greater than 1, the graph is a horizontal compression. When omega is between 0 and 1, the graph is a horizontal stretch. When omega is negative, the graph reflects about the vertical axis. When omega is 1, it's just the sine function. Changing omega changes the length of the period of the graph of the function. Okay? If omega is 0, the function is a constant. It's a line, y equals 0. So we've done 2 of them. We have 2 more to do. Okay, here we are going to translate our sine function with just the k function. If you remember the first slide that we had said that k had translated your regular sine function up and down or vertically. So the first thing we drew is in green, it's just y equals sine x. And if you look, I'm still going between 0 and 360. So we have one period between 0 and 360. We didn't change that. Those are all the same. Now we're just doing a +2, a +3, and a +10. K shifts the function up and down. When k is positive, we're going up. And we'll show you the next slides. When k is negative, we go down. So for this first one, we have a plus 2. So look at that. I went up 1, 2. Okay, then I went up 1, 2, 3 for the next one, and up 10 for the last one. And that's where I start. Okay, I start at 2, or I start at 3, I start at 10. And we still go up 1, down 1. Okay, our midline here would be y equals 10. Our amplitude is 1, because we just have a 1 in front of the sine. Here my midline is y equals 3. Okay, my amplitude is 1. Here I kept it as sine x plus. I just put in -1. I know that's not how we would normally write that. We would write sine x minus 1 or sine x minus, minus 2. So here we just dropped. We just dropped by 1. My scale changed. That threw me off. If we went from 0 to -2, I zoomed in more than I thought I did. So here is -1. Our midline is y equals -1. Our midline here is y equals -2. Our amplitude is still 1, just because the scale on the y-axis is a little funny. Okay, plus 1/2, plus 1/5. You see my scale is still pretty small. So here's 1. 1/2 is the red one. So we're starting right here. If this is 1, that's 1/2. So the red one starts at 1/2. The blue one starts at 1/5. The black one starts at -1/3. Okay? It just shows your vertical shift. So just to summarize what we did here, the value of k controls the vertical translation of the sine function. It's translated vertical by k units. Okay, vertically when k is greater than 0. That's not right, sorry. The graph is translated in the positive direction up compared to the graph of the sine function. When k is less than 0, the graph is translated in the negative direction down compared to the graph of the sine function. If k is equal to 0, the graph is not translated, and it's about the midline y equals 0. We'll see in the final slide that our midline always works out to y equals k, which they don't explicitly say on this slide. Okay, now we're doing h. The h value does the horizontal translation, okay? And you notice we're in pi's here, so my x-axis is not from 0 to 360. So our blue one is sine x, which is the base one we've been looking at a lot. If I translate it by negative pi, my original equation is -8. So it's really x plus, it's x minus pi, so h equals pi. Here I really wish I could have gotten an x-axis that was drawn with pi's in them. Well, let's just do it here. This would be pi, and this would be 2 pi. Okay, at the maximum we're at pi over 2, and at the minimum we're at 3 pi over 2. Okay, so I can erase this. I'll just erase, I can't erase that. So if we're shifting by pi, that means we're shifting our graph to the right in a positive direction. So what we see here, instead of starting at 0, we shift it to the right, and we start at pi. Okay? So instead of starting at 0, we start at pi. Okay, here I kept the sine equals x minus pi because the next one is sine x plus pi. So that really means that we're shifting it a negative pi. That is left in a negative direction. So here we're at pi, 2 pi, etc. If we're shifting it to the left, pi, it's the same as shifting it to the right as far as the picture goes. So your picture is not going to change. What we really would see is over here, this would curl down, and I'll do it in blue. Okay, there's our pi, and we shifted to the left. Okay, it gets a little harder to read when we're doing fractions, but basically we're shifting pi over 2, positive, to the right. So this green one, here's pi. This is pi over 2 because it's the maximum of the original sine function. So we shifted pi over 2 was our starting point for the green line. Okay? For here, we're shifting negative pi over 4, which is obviously negative, and to the left, which we can't see our beginning point right over here. But we didn't shift a full pi over 2, a full 90 degrees. We shifted a quarter of that. You can't see 2 pi shift. Because that's where we are, is 2 pi. So if we shifted to 2 pi, we took a whole cycle and just shifted it a whole cycle. Okay, now we switched from pi's to numbers, and it still works the same with the purple one. H is 2, which is positive to the right. You can actually see our starting point is 2. Okay, for the next one, our starting point is is 5. And if we look at that one backwards, we would have a negative 5 over here. No, sorry, 5. So we shifted it 5 to the right. I don't know what we would have over here. So we're at 1 point something. We have to find what that is over there. But our starting point starts at 5, and that's what's important. We can, mirror it over here, but our starting point shifted positive to the right. Still going. Here we're shifting to the left. So the first one, h equals negative 1. That's our light blue one. Our negative 1 is over here. Negative 2, I should have copied this at a different spot in the graph, would be negative 2 to the left, negative 5 to the left. And you can read that on your x-axis because your x-axis are true numbers. In summary, the value of h controls the horizontal translation of the graph. If h is greater than 0, the graph is translated to the right in a positive way. If x is less than 0, or to the left in a negative way. If h equals 0, the graph isn't translated, and it starts at x equals 0, just like a regular sine function. Okay, here's your summary. Read through it. Some highlights. Absolute value of A is the amplitude, and this is how you calculate it. Okay, the amplitude is the distance between the maximum point and the midline. So A is the difference between the maximum and the midline, or it's the maximum minus the minimum divided by 2. Either one works. 2 pi over omega is the period of the function. The period, capital P, is the distance between two consecutive maximal points. Right there is period. Omega over 2 pi is the frequency of the function. The frequency is the reciprocal of the period. H is called the phase shift. The graph of y equals k is the midline. Furthermore, the graph of the sinusoidal function f is obtained by vertically scaling the graph of the sine function by a, horizontally scaling the resulting graph by 1 over omega, then horizontally and vertically translating the resulting graph by h and k units respectively. Okay, that's how we're graphing. I'm going to pause here and save it. We're going to try to do this one in 2 pieces because it's a bit long. So this was really the information, and then we're going to do some practice problems next.